This is the first part of 8086 assembly language programming. So first we will start with what are assembler directives and operators. So any assembly language program requires an assembler to get it converted itself to machine code so that it can run in a machine. Okay, so for again 8086 we have assembler for that. So whatever instructions we studied earlier through various videos, right, along with their operands, they have to be given to the assembler in a particular structure so that the assembler may do some background work so that a proper machine loadable code can be generated. Okay, so this background work or setting up the environment required for running a program is made possible through assembler directives. So as a programmer, you have good control over how this environment is set up, like how much should be the size of each segment, maybe what all should be the content of each segment, like that. Okay, so that's the beauty of assembly language code. So those control a programmer can enforce through directives to the assembler. Okay, so that's the main way. And also assembler directives bring a structure to the program. So let's see what is a typical structure of 8086 assembly language program. So 8086 assembly language program will have segments within it, and each segment will have the things that are supposed to aid execution or to be executed. So this is the bare minimum segments that I have shown here. So every code or every program will have data segment and code segment. So this is how you will define the segment. You will give a name or a label to the segment followed by assembler directive segment, right? So this section indicates the start of data segment. Now how will you mark the end of data segment, or how will you mark where the contents of the data segment terminates? So that is again using another assembler directive ends or end of segment. So again you have to use this label, then give a space and put ends. So this is how you define the segment. You give a name to the segment, then write the assembler directive segment, and you demarcate the end of the segment using the label again and using the assembler directive end of segment. Okay, similarly we have another segment whose label or name is code, which starts over here and ends over here. And one main thing to note here is now the assembler doesn't know that this is the data segment that we meant and this is the code segment that we meant. So that is made clear through this line. Okay, so the assume assembler directive will help the assembler to load the registers or base registers which are used to address individual segments properly based on the directive given by the programmer. So here our directive regarding data segment is our data segment's name is data. Okay, so it will be created somewhere in the primary memory and it will be given an address. So that address has to be loaded into the base register DS so that elements that we define within this data segment can be accessed. So that is done through this assume directive. So similarly the code segment, again we have to mark where the base of the code segment starts and we have to put it in CS, right? So that is done over here. So this assume directive is very important. Apart from segment declaration, it will actually link the start of segment to the base registers which are required for executing a program. Now what all things can go inside each segment? Within data segment we can have labeled storage, like in higher level programming languages we define variables with user-friendly names, right? So such things you can do within data segment. And what all things can come inside code segment? The instructions that we studied earlier, right, that along with their operands you will write within the code segment, and even the procedures that you create will be defined within the code segment. So the procedures and how they can be declared and used, that we will see in a sample program. So this is the typical structure. You will demarcate segments or name different segments. You will link the segments to the base registers. Then finally, to indicate the end of your assembly language program, you will give another assembler directive end. Okay, so these things should be present in every assembly language code. So let's see a sample 8086 assembly language program to add two immediates. Okay, so my intention is once I add the two numbers, and most probably I'll get the result in X, right? I have to preserve that result so that I can reuse it maybe for another operation. Okay, so as you know, the registers are volatile, so it can't hold the result as it is, because many of the instructions that we execute, right, they will alter the register and we may not even catch that. So once you have a useful result within a register, you have to move it to a permanent storage, so it's better to keep it in RAM. Okay, so what we do is we actually foresee that, and we decide that we will have separate space in RAM to store our result. Okay, so within data segment we will write a label named result. It's a user-friendly name, and maybe I'll define a word space that is 16 bits for that. So how much words that you define, that you have to specify over here. Okay, so here note that the DW is an operator, assembler operator, that we use to specify or allocate the space. So here the meaning of this line is result is a labeled space in primary memory of size 16 bits. Okay, because only one word in length. Okay, so that's the only thing that we need to define in data segment. So data segment effectively has the things that we do with the RAM. Okay, now let's see how the code works. So the code segment is demarcated by this code segment and this code ends. So we have to load the two numbers in registers and then we have to add. So maybe 5 and 3, I'll add 5 and 3. So 5 is loaded into X, 3 is loaded into BX. Now I add BX to X, result will be in X, and I need to preserve the result. So I have already a space in RAM with the name result. So move result to X. So it will result in moving whatever is in X to a result. Then I am ending the code segment and ending the program. So the beauty is, once this program ends, and maybe if you have the address of result with you, and if you go and see the location, you can still see the result of addition. And also, even if you load another program and run, and provided that program doesn't overwrite this area, okay, even though the registers change, you can see the result. Okay, so this is one of the important takeaway. Whatever you have to preserve, try to put it in RAM.